Let's get started today's class. So from now on, we explore about some memory systems in the computer system. So actually, in the previous class, we covered how to handle exceptions in the pipeline processor, and then I explained that usually. So we expect that our processor supports a precise exception. The precise exception means that the exceptions are handled by the instruction order, not the timing order. Okay, so which means that the exceptions should be handled. So we can. So actually, the processor can deduct exceptions out of time, which means that actually the detection of the exception is not same to the order of the instructions, because we have pipeline, the multiple pipeline stages, but the handling of exceptions should be processed by the order of the instructions. Okay, so which means that the processor needs to handle the exceptions in the instruction order. So that's the precise exception. Okay, so also we briefly explored some real processor architecture of ARM processors or Intel i7 processor. And then actually, in the previous class, I showed the ARM Cortex-A53, right? 53 processor. So this is the so actually this ARM Cortex-A53 implement the static pipeline. So which is very similar to our 5-stage pipeline architecture, because so our 5-stage pipeline architecture is called the statically scheduled pipeline architecture. Actually, this is the actual name of this 5-stage pipeline architecture. So I repeat, the statically scheduled pipeline architecture. But the most of the modern processors use out-of-order processing, and then this out-of-order processing is called dynamically scheduled pipeline architecture. Okay, it's a different. So actually, the Intel core architecture uses the out-of-order processing, which means the dynamically scheduled pipeline architecture. So this is some advanced level of the discourse. So we will not cover the out-of-order processing in this course. Okay, but in the previous class, we saw some performance of benchmarks by Cortex-A53, and then we found that the performance actually, so our processor cannot reach the ideal performance of the processor, right? So I showed that the ideal performance of the Cortex-A53 is about the CPI is 0.5, but because of the pipeline stall, the actual performance of this ARM processor is about the 2x times slower than the ideal performance. And if we just consider the delays by memory system, then we can find that the performance is degraded very much. Okay, so the previous results showed that the performance of memory system is very critical for the performance of overall computer system. Okay, and then in chapter 5, we will learn about the memory systems. Okay, the title of this chapter 5 is the memory hierarchy. Actually, so sometimes we call memory systems as memory hierarchy, because the memory is organized as the hierarchical levels in the computer systems. Okay. Okay. Before diving into the memory system, let's see the locality of our application. So the title of this slide is Principle of Locality. So actually, in some Korean textbook, locality is translated as 지역성, but I don't think that's the good translation. Actually, we can understand the locality as locality. So locality means that if some data or something is frequently accessed, then we can access the same data or neighbor data repeatedly in the future. Actually, that's the definition of locality in a computer system. Okay. So this line also explains the locality in the computer system. So programs, actually the instructions are executed in a processor. So actually our program access very small amount of data repeatedly. Okay. Even though the memory size is very large, or even though the storage size is very large in the computer system, our program, so a single program just accesses the small amount of data. Okay, and then this is called actually locality. Okay, so for example, so let us assume that how can I take an example from the earlier application? So think like this. So let us assume that our Office program, like Word or PowerPoint, the size of the file of this Word or PowerPoint is around, let us assume that around 100 megabytes. But in a short time period, this program just accesses a small amount of data repeatedly, not an entire 100 megabytes of data. So this is called the locality. And then there are two kinds of locality. Okay. The first one is the temporal locality, and then the second one is spatial locality. So in the English word, temporal means some time related, and then spatial means the space related. So we can say that the temporal locality is the time related locality, and then spatial locality means the space related locality. Okay, so let's see the definition of the temporal locality. So temporal locality means that if a data or an item is accessed, and in the near future, the same item or same data will be accessed with high probability. That is the temporal locality. So, in other words, temporal locality means that the same data is accessed repeatedly, again and again and again. So we can find the example of the temporal locality in our code. So for example, if we use the iteration for loop for I equals 0, and then I is less than 100, and I plus plus, and then A equals P plus C. So if we see that this program, this example, then we already know that. So this statement is repeatedly executed in our computer system. So in order to access to execute the same statement repeatedly, which means that instructions in this iterative loop is repeatedly fetched from the instruction memory, right? Because the same instruction is repeatedly executed in a processor. So what does that mean? In chapter 2, so I explained that instructions are also data. So which means that the instructions are also stored in the main memory of the computer system. In order to execute instructions, we need to fetch. It means that we need to read instructions from the memory. And in order to read the instructions from memory, then we need to give the address of the instruction, so which is program counter. And then we can read instructions with this program counter. So think like this. Well, the same instructions are fetched again and again. So which means that in the memory, the same address is given to this memory because it's the same instruction. And then a processor reads the same data, which is instruction, with the same address. So which means the same data is repeatedly requested by a processor, which is temporal locality. Okay, this is the temporal locality. So which means that the same data is repeatedly requested and accessed by a processor. And then how about the spatial locality? So spatial locality means that if a certain data or a certain item is requested by a program, high probability, the program will request the neighbor item or neighbor data. That is the meaning of spatial locality. So which means that, oh, this is a certain data. And then this data is stored in the memory here. And then the same program will access the neighbor data in the near future. So it's possible that if this A is accessed and then the same program can access some other data which is far from this data A, but usually, so I said that it's with the high probability, but usually if this data is accessed, and then in the near future, the neighbor data will be accessed. So that is the definition of spatial locality. So that's the example of the spatial locality. Also the instruction. So if we see the instructions, then PC, the next PC is the PC plus 4. So which means that when a certain instruction is fetched from the instruction memory, then with a high probability, the next instruction, the address, the differences in the address is just 4, that's the neighbor data. So we will access the next instruction, which is the neighbor data. So, and then the another example is array data. So, for example, so we frequently use the array data, and then for this example, in the iterated loop, so we can calculate the AI equal BI plus CI, and then the I is incremented by 1. So, but actually we already know that how the array data is stored in the memory, right? So this A0 is the base address of this array, and then A1 is stored in the A0, so the base address plus some offset. So we know the offset is the size is equivalent to the size of an element. But we can say that this data is the neighbor data. So if we see that this code, then we already know that firstly the A0 is accessed, and then A1 is accessed, A2 is accessed. So which means that in the near future, then the A0 is accessed, and then in the near future, we can expect that A1 will be accessed. So this is the spatial locality. So there are two kinds of locality, and then actually, so we can check the locality of our data or our program. in time related or space related. And then these two kinds of localities are observed in our normal application, in normal data. Okay, so why did I explain this locality? Because a memory hierarchy exploit locality. Okay? So this locality is the observed characteristics in our application. And then based on these observed characteristics of our normal application, researchers design memory systems, which is the memory hierarchy. Okay, but actually the locality is frequently found in our real life. So I will explain later about some locality in the memory hierarchy and then in our real life. Okay. Okay. So computer systems take advantage of locality to improve the performance. Okay, because we can the computer systems exploit locality to improve the performance. So actually we organize memory system as the memory hierarchical structure. So in order to increase the performance of a memory system. Okay, and then memory hierarchy actually exploit the locality observed in our normal applications. So, for example, let's think about some normal program. So we already know that the normal computer systems have very large storage devices. So, for example, so in the normal computer system, the size of the storage is around 1 terabyte or 2 terabyte or even 4 terabyte. But if we see the size of the main memory, the size of the main memory is also large, but the size of the main memory is much smaller than the size of the storage devices, right? So about the 4 gigabyte, 8 gigabyte, or something like that. So how can you use locality? So actually, in storage, we have a large amount of data on the storage. But in a computer system, when the application is run on our computer system, this application just read the small amount of memory from the storage to the main memory. So which means that even though our storage have a large amount of data, only small part of the data is moved to the main memory. Then our application make use of this data on main memory. So it's kind of locality. Even though we have large data, but when we use an application, we just use the small amount of data, the part of data, right? Even though we have many files in our storage system, we just use the specific file, right? So we also make use of locality in our computer system, like the storage system and the main memory. But here focused on the hierarchy of the memory. So this is the memory hierarchy. So it looks like the pyramid. So actually, you can find the register file on the highest level of this hierarchy, and then you can find the storage devices here in the lowest level of the hierarchy. And then you can find the main memory and cache is here. So what does that mean? What is the memory hierarchy? So hierarchy means It's hierarchy, actually hierarchy, but in Korean it means the 계층 구조, 약간 신분 이런 걸 뜻하긴 하는데 in Korean, but we can so which means that the hierarchy has higher level. This is the higher level, and this is the lower level. Okay, so which means that based on the different level of the memory hierarchy, the memories have different characteristics such as the performance, cost, and size. So one, everyone wants good memory, right? What is the good memory? And what is your good memory? Let's define it. Why is a good memory? So what is the characteristics of a good memory? It's fast, and we want to store large data in our memory. So which means that the size is very large, and we want cheap memory, right? So everyone wants fast memory, large memory, and cheap memory. So this is an ideal memory device, but in the real world, you cannot find an ideal memory device, right? You cannot find any ideal things in our real life. So what does that mean? So we can find the RF is a register file in the highest level of the memory hierarchy. So we already know that the register size of the register file is very, very small, but the register file is very fast. So which means that the speed of the register file is nearly same to it's really shorter than the clock period, which means that the speed of the processor logic. Okay. So register file is very fast, but no, the register file is very small. Also, it's very, very expensive. Okay. But usually in the memory devices, small memory is faster. So which means that, so usually for the register file, we can use flip-flops or we can use SRAM. It's a static RAM. But if we increase the size of this SRAM, the speed is slow. So speed is just slowed down. Okay, so which means that the speed becomes very slow. So that's why the size of the register file is very small, because the processor requires the very fast register file with high performance. Also, we can find the different levels of cache memory here. So actually, you can find the L1, L2, L3 caches. So cache also have several levels. So actually, level 1 cache is in the higher level. The L2 is here, L3 is here. Okay, so there are different levels of cache memories. So also, we can expect that. So in the higher level, the memory speed is faster, but the size of this memory is smaller. So we can expect that, oh, there are different levels of cache memory here, but I already explained that the level of cache is in the higher level of the memory hierarchy. So this means the size is small because it's a higher level, but it's fast. In the level 3 cache, the size of level 3 cache is a little bit larger than the level 1 or level 2 caches, but it's slower than the level 1 or level 2 caches. So if you are interested in the some CPU processors, then you can read some specification of the CPUs. Then you can find the size of the level 1, level 2, or level 3 caches in the Intel or AMD processors. And then you can find that the level 1 cache is the size of the level 1 cache is around 32 kilobyte. And then level 2 is larger than the level 1, but it's at the 256 or 512 kilobyte. Level 3 cache is very large, like several megabyte. Okay, so you can have different levels of cache memories. But when I explain about the processor in chapter 2, so I mentioned register file, or also I mentioned main memory, but I did not mention caches. So actually, no more instructions, just change the register file or main memory, the content in register file or main memory. Caches are managed by hardware, not software. So actually the hardware automatically manages data in these cache memories. Okay? So we will learn why cache memories are required in the computer system data. Also, under this cache, you can find the main memory, DRAM. So we already know the size of the DRAM, like 4 gigabyte or 8 gigabyte in the computer system. So the size of the DRAM is also much larger than the size of the cache memory. But it means it's very slow. Also, in the cache, so you can find the cache memories is inside of the processor chip. But we can find RAM outside of our processor chip. So if memory is located outside of the chip, then this means that it is very slow. So if memory is located inside of the chip, this memory is very fast. But we cannot use the chip memory in the processor. So usually we use the SRAM, the steady RAM, for this cache memory, but we use the DRAM, so dynamic RAM, for the main memory. And then actually, SRAM is much more expensive than the DRAM also, but SRAM is faster than the DRAM. The size is small because it's very expensive, but the SRAM requires the more hardware resources. And then DRAM, actually the semiconductor process for manufacturing DRAM is totally different from the manufacturing process of processor logic. Okay. So DRAM is here. So actually we use the DRAM as the main memory of the computer system. And then under this main memory, we can find the storage like SSD or hard disk drive. So we can know that the size of the storage is very large compared to the main memory, but it's very slow. So usually the hard disk drive is much slower than the SSD, but SSD is also slow, 1,000 times slower than the DRAM. So, but what is the benefit of these storage devices? It's a low cost. The performance is even though the performance is very low, but these storage devices support high capacity. So also another feature of these storage devices is the non-volatile. Non-volatile. So which means that even though we turn off the power of the computer system, the data exists in these storage devices. But the DRAM is the volatile memory. So which means that the data is removed if the power is turned off. Okay? But in the memory hierarchy, these memory hierarchy have multiple levels, and then we can find the expensive memory devices, and then high performance memory, and then low capacity memory in the higher level. And then we can find low cost memory, and then low performance memory, and then high capacity memory in the low level of the memory hierarchy. But question, why do we organize memory devices like this? Why then? How can the why do we use memory hierarchy? So why did I explain locality before explaining about the memory hierarchy? It's because the size of the memory is small, but I explained it because of the locality, the program. So within the very small time window, our program accesses small amount of data again and again, repeatedly. What does that mean? So if we see the our program, so usually the program starts with the load instruction. So this load instruction, the data is transferred from the main memory to the register file. And then we already know that the most of our instructions can use the data in the register file and then stores the also the result to the register file. Okay. So, but in order to process some data, then we first need to transfer data from the main memory to register file, right? But if a program just use the small amount of data, and then if this small size of memory is fast, then we can store the frequently used data in the small memory, right? Because this data will be repeatedly accessed by the program with the load instruction. So what's the benefit? So actually, actually, we assume that when the load instruction is executed, and we assume that this load instruction can read data from the data memory within one clock period. So that's our assumption. This assumption is actually not true. So actually, the memory we learned in the chapter 4 is the level 1 cache. The size is also small. The main memory is located outside of the processor, and the size of the main memory is very large. But if we can find the frequently used data in the very small size of the memory, then we can access this data very quickly, which means that we assume that the cycle for reading data from the memory is 1 clock, but actually, if the data is found in the main memory, the required cycle for reading the data from memory is about 100 cycles or even thousand cycles. Okay, so which means that when the load instruction is executed, and then if the data is found in the main memory, then the next instruction needs to wait 100 cycles or even 1,000 cycles. And then the processor does nothing because the next instruction cannot be executed because of data dependencies, right? So that's the problem actually. So that's why the memory system performance is very critical for the entire performance of the computer system. But if we can find the frequently used data in the very small cache memory, then we can access this data very quickly. So which means we can wait around the 1 cycle to access data from this cache. If the data exists in this cache memory. So, but we can because the locality is observed in our normal application, we can use this memory hierarchy. So which means that if the locality is not observed, then the efficiency of the memory hierarchy will be very low. But fortunately, we can find very high locality, and so we can find strong locality in our normal application. So we can use the memory hierarchy to improve the performance. Okay. So and then let's see another terminology: hit and miss. Okay, hit and miss. So actually, I already explained about the hit and miss in the branch prediction, right? So which means that if the prediction is correct, so we can call it as hit. And then if the prediction is incorrect, then we can call it as miss. So we can use the same terminology, hit and miss, in the memory hierarchy. So, let's think like this. So this is the load instruction. So x1, 0, x2. So with this address, then processor execute the load instruction. But I explained that computer systems use memory hierarchy. So which means that there are different levels of memory devices or memory components. So first, when this load instruction is executed in the memory hierarchy, we can find the caches. I frequently use this $sign for the cache, because the pronunciation of the cache is actually the same to the cache, which means money. So I frequently use this $sign. Okay, and then actually many people use the $sign for the cache memory. Okay. So when the load instruction is executed, then the processor first search for data in the cache memory. Okay. So, but this cache memory is the temporary storage space. What does that mean? When this load instruction is executed, actually the definition of the load instruction is that the load instruction will access main memory, and then the data will be transferred to the register 5 when the load instruction is executed. So which means that the data will exist in the main memory. But how about the cache? The cache is the actually temporary memory space. What does that mean? Actually, the processor stores the frequently used data in the cache. You understand? So this is the temporal memory, and then because the size of this cache is much smaller than the main memory, we can just store the frequently used data in the cache. Which means that when this load instruction access the cache memory, the required data can be found, or the required data is not it can be possible that the required data is not found inside of the cache. Do you understand? When the load instruction accesses the main memory directly, then we can find the required data. But you know, the cache is the temporary storage, temporary memory, which means, and then the size of the cache is much smaller than the main memory. So which means that when we access this cache, the required data can be found or not. There are two cases. So if found, then which means that, so if data is found inside of the cache, then the processor can read data from the cache because it's the same data. The same, but So the processor think that, oh, this data will be frequently used in the future. So this data is stored in the cache. And then if this data is found in the cache, then processor can read this data from the cache quickly. Okay. So if found in the cache, then we can say that this event is hit. So this is the very happy case, right? The processor can read data quickly from the cache. And then another event is the if not found. This event is called miss. So if the required data is not found in the cache, then the processor also needs to access the lower level cache, so lower level memory. Okay. So and then this processor is repeated. So if the required data is not found in the level 3 cache, it's called the last level cache. Then the processor needs to access the main memory, and then the data will be found in the main memory. So this means that there's a certain level of a processor access a certain level of memory for the requested data. But this requested data is not found. So in this case, we need to access the lower level memory to find the requested data. Okay, this is the miss. But this is the untapped case because the data is not found in the higher level cache or higher level memory. So, and then we need to access the lower level memory or lower level cache, and then it will take longer time, which means that it the processor needs to more cycles to fetch data from the memory, right? So need to wait, which means that the cycles are wasted. It's an unhappy case. Okay. So there are two possible cases, like hit case or miss cases. Okay. So we can define the hit rate like this. So this is the memory, like cache or some like cache, and then we can access memory for some load and store instruction. And then we can say that there are two possible results, like hit or miss. So hit rate means that it's the total number of accesses. So hit count is divided by total number of accesses. That is the hit rate. So for example, a processor can access cache 100 times, and then the hit count is about the 40, and the hit rate is around the 0.4. It's a 40%. Which means that a processor can find the required data in this cache with the 40% of probability. Okay. So we learned about the hit and miss in the hierarchy. Okay, and then I will briefly explain about the memory technology. So actually, here I explained about the memory hierarchy and then the basic terminology and the basic definition of the memory hierarchy, and then I will explain about the memory technology. Also, because our nation, Korea, is actually rely on the memory technology industry for their economy, right? Samsung Hynix is a very big company in the memory. Okay, so there are many kinds of memory devices. Okay, and then in the computer system, we frequently use the static RAM, called the SRAM, or dynamic RAM, it's called the DRAM. So we can use the magnetic disk stuff, hard disk drive. Also recently, we can use the flash memory. or SSD, solid state device, solid state drive. Okay, but so why do we use these various kinds of memory? Because we cannot find any ideal memory devices in our real world. Okay? So for example, the standard RAM, supposed as RAM, it's very, very expensive. So it's very expensive, but this is the typical latency of the SRAM. So which means that if the request is given to this SRAM, the latency means that, and then this RAM, this memory can return the data to this some processor. So, and then this elapsed time is called the latency of the memory. Okay, so time between the request and service. So if you see the latency of this SRAM, it's about the nanosecond time. Like, so it's lower than, it can be lower than the 1 nanosecond, but it's around the several nanoseconds. But if you see the cost of this SRAM, it's very, very expensive, right? So actually we can build the SRAM method in typical data center technology. It's same to the semiconductor technology which is used for building AC, so it's a normal chip. So and then usually to build the SRAM, it usually require 6 transistors. So that's why the SRAM is very expensive. Okay? So usually we use the SRAM as the internal memory of our chip. And how about the DRAM? So DRAM is called the dynamic RAM, but you can find that the latency of the DRAM is about the tens of nanoseconds. It's about 10 times or more than 10 times slower than the SRAM. So, but the DRAM is, the cost of the DRAM is much lower than the SRAM. So that's why we use the DRAM as the main memory. So as I explained, the process technology of the DRAM is different from the normal edge technology. So that's why we locate the DRAM outside of the processor chip, which means it's slower. So how about the magnetic disk? The latency is the millisecond time. Very, very slow compared to the CPU. Okay, very millisecond unit, so it's very, very slow. But the cost for storage is very, very low, so that's why we use magnetic disk as the primary storage devices. Okay. So what does that mean? We cannot find any ideal memory devices in our real world, and then because of this, we can organize the memory hierarchy to improve the performance. So which means that we can use the small memory to access this frequently used data very quickly. Okay. Then I think it's the so I briefly explain about some DRAM technology. So DRAM looks like this. So this is the MOS transistor, and then this is the capacitor, the brown. It's a capacitor, it's an MOS transistor, and then actually the most of the memory looks like this. This is the word line, this is the bit line. And then using this word line, so this MOS transistor is turned on or turned off. And then actually the data is stored in this capacitor. Okay. So charges are stored in this capacitor, and then if this And the charges are stored in the capacitor, and then if the one line is turned on, which means that the NMOS transistor is turned on, then the charges in this capacitor is moved to the bit line. So which means that we can read the different voltage level because the charges are moved to this bit line. So that's how the DRAM is working in the computer system. Okay, it's the kind of low-level technology to the computer science students. But DRAM looks like this. So which means that DRAM actually requires one DRAM cell requires one NMOS transistor and one capacitor. And then in this one DRAM cell, we can store 1 bit of data. Okay. So DRAM cell looks like this, and then this one line is activated by address, and then so the processor can read the data from this DRAM cell. Okay. So usually we use the DDR DRAM for the main memory of the computer system. So DDR memory means that it's double data rate RAM. So which means we can read and write data at the both edge of the clock signal. Okay, right? Rising edge and then falling edge. So for the graphics processing unit, the GPU, we use the QDR device. So QDR means that it's quad data rate RAM. So which means that we can read and write data at the 90-degree phase of the clock signal, like 0 and then 90 degree, and then 180 degree, and then 270 degree phase of the clock signal, QDR. So, and then this technology is used to increase the bandwidth from the DRAM devices, right? And then, okay, let's see the some performance of the DRAM. So this table shows the capacity of the typical DRAM chip, and then also the cost per gigabyte. As technology advances, so we can say that the density of the DRAM is also increased, which means that the cost per 8 gigabyte is decreased. Okay, so which means that we can use the very large DRAM, so we can enjoy the large space of DRAM devices. But so it's related to the some what can I say, reliability of the DRAM. So as I explained, this is the structure of the bit cell of the DRAM. And then, you know, the DRAM is composed of one NMOS transistor and then this capacitor. And then, if the size of this bit cell of the DRAM is reduced, so which means that the size of the NMOS is reduced, also the size of the capacitor is reduced. So we can say that this is the switch. Okay. But if this switch size is reduced, then which means the charges inside of this capacitor can be dissipated. So if the charges are dissipated, then the data is removed from this capacitor. Okay, data is erased. Okay. So then that's the possible. So we want to store some data to our DRAM, but because of the lower reliability of the DRAM, the data can be erased. So that's another research topic in the DRAM devices. So and then also actually in the DRAM devices, these charges are continuously dissipated to the bin line. So that's why we need the refresh in the DRAM. And then because of this refreshing, the performance is also degraded. But usually, as the technology advances, we can enjoy the large DRAM. Okay, let's keep here. And then this is also important. So this is called the memory level parallelism. So what does it mean? So actually, the memory, the bandwidth is very important. But usually the performance of the memory is lower than the performance of processor. So what does it mean? So let's think like this. So let us assume that we want read the 16 byte from the memory. Okay. So how can we read data from this memory for 16 byte? So we can read 1 byte of data sequentially from the memory, right? So which means that we can give 16 requests of 1 byte of data to the memory, and then we can receive the 1 byte of data from the memory sequentially, right? So this is one worldwide memory organization case. So we can give the request to the memory 16 times for 1 byte of data. So what's the problem? So in order to read the 16 byte, then we need to consume 16 requests. And then I also mentioned that the memory speed is slower than the processor speed. So let us assume that it's how can I say? So the latency of this memory device is about the 15 cycles. So it's a very low actually. So for this one worldwide memory, then in order to service 16 requests, then it will consume 16 multiplied by 15 cycles. Okay. So which means that the processor send request to the memory and then wait 15 cycles, and then the processor can receive 1 byte of data from the memory. And then after that, the processor give another request, the next request to the memory, and then wait for 15 cycles and then receive the request data. But how can we improve the performance? One simple way is to increase the memory bus, which means that we can use the large memory bus, and then which means we can give one request for 16 bytes of data. So what's the benefit? The processor can only send one request for the 16 bytes of data, and then wait 15 cycles, and the processor can receive 16 bytes of data. So it will cost only 15 cycles. But problem is that if we use the larger burst, then the cost will be very expensive. The cost will be very high. So actually, it's very important for the chip design. So this is the processor, and this is the DRAM, and then DRAM is the external memory. So which means that the processor and then DRAM is connected via the metal line on the PCB board. But usually, and then the pins of this processor chip and then DRAM chips are connected to this metal lines. Usually, pins are very expensive. Okay? So everyone wants to decrease the number of pins on the chip because the pins are very expensive. The problem is that if we use the larger burst, then we need to use the larger number of chips and larger number of pins. So which will be very expensive. So this is the very simple way to improve the performance, but this solution is very expensive, so we can use it. But the performance of the memory device is very low. So how can we solve this issue with the lower cost? So for example, think like this. This is some person that give request, and then this is some service people that respond to the request. But this person is much slower than this requester. And how can we increase the performance for this case? So this is the very fast person, but this is the very slow person. So how can we increase the performance? One way is we can increase the service people, because this is the slow. How can we can give the first request to this service people, and then instead of waiting the data from this B, we can give another request to the slower person B, and then we can give another request to the person B, another people, yeah. So by doing this A can give request frequently. So which means that the A can give many requests, and then while waiting for the service from some B, then A can also give requests to another service people, P1, P2, and P3. And this colors can be also applied to the memory devices. So processor is very fast, but memory is slow. So this is the process, and this is the memory. So instead of using one memory, then the memory can have multiple blocks. And then processor can give the request to the block, the first block of the memory, and then the processor gives the next request to the second block of the memory, and then give the processor can give the repeated request to another blocks of the memory, and then the processor is the fast people. So when the data is serviced from the memory, then this data will be also returned to the processor sequentially. Okay. So this is called the memory level parallelism. And then we can implement this memory level parallelism with multiple banks. Okay. So you can find here the bank number 0, bank number 1, bank number 2, and bank number 3. But you can find that if you see this width of the bus, the width of the bus is identical to this width of the bus, the organization A. So which means because the processor is very fast, the processor can give the request to the memory bank 0, and the next cycle, the processor gives another request to the memory bank 1, 2, 3, and then after that, after some latency, the data is returned from the memory sequentially from A, B, C, D, like this. So this technique is called the memory interleaving. So which means that we can use the multiple memory banks. So actually bank means the independent memory block that can respond to the request from the processor. So by using the memory interleaving technology, then we can use the smaller bus, so we can also increase the performance from the memory. Which means that the memory, this memory is working. So multiple memory banks are working for the multiple requests concurrently. So this is why this technique is called the memory level parallelism. Okay. Actually, this technique, so so we can apply this technique in our real world, right? So fast agent and then some slower agent is here. So fast agent can give the multiple requests sequentially to the slower agent. Okay. Okay. Let's see the another memory technology, flash memory. So actually, recently we used the flash memory as the storage media for SSD, the solid state device, solid state drive. Okay. And then everyone knows that SSD is much faster than the hard disk drive because the hard disk drive is actually a mechanical drive. So which means that the hard disk drive has the flat drive. It's called. It looks like some plate, and then so the data is stored on the surface of the plate. And then actually, when the data is requested, then the head of the hard disk drive needs to find the location of the data. So this is the mechanical mechanism in the hard disk drive. But the mechanical device is usually much slower than the solid state devices, electrical devices. Okay. So flash memory is so do you know the EEPROM? EEPROM. So as you can see, this EEPROM is the read-only memory, but it's electrically erasable. And, sorry. So I forgot the abbreviation of the EEPROM, but actually we can erase data of this EEPROM. And then the ROM means the read-only memory, which means that we cannot write data to this ROM. But EEPROM is different. We can erase data on the EEPROM, and then after this erase process, then we can write new data to the EEPROM. So actually, the structure of the flash memory is very similar to the EEPROM, which means that after erasing some data on this flash memory, then we can write new data. A little bit, but so actually the EEPROM, so actually the erase requires very high energy, so which means that for this erase process, it will take very long time. But the flash SSD is very fast, so we can apply some technique for this SSD, but I will not explain in this time. So what we can say that so we use the flash memory as the main storage medium in the SSD, but it's, as you can see, this is the chip, which means that this chip is very much faster than the hard disk drive, but the latency is higher than the DRAM, so about 1,000 times slower than the DRAM. But because the performance is about 100 times or 1,000 times faster than the hard disk drive, so if we use this SSD, then we can increase the performance of our computer system. Okay. So there are also two types of flash memory, like the low flash and then the flashy. So for the disk drive, we frequently use this and the flash memory. And then for this low flash, we actually the low flash looks like a typical DRAM, but so this this is good for the random read-write accesses, but it's also very expensive compared to the NAND flash memory. So we frequently use this NAND flash memory as the main storage media of the SSD. The hard disk drive, as I explained, the hard disk drive is the mechanical device that stores the data on the surface of the disk slip. Surface of the plate. Sorry. Okay. So you know this is the inside of the hard disk drive. So actually, this is the head of the hard disk drive. So our data is stored on the surface of the plate. So which means that in order to access the data, then we need to move this arm of the hard disk drive. So which means that we need to change the location of this head. So this is the mechanical process. So which means that it's very, very slow compared to the SSD. Okay. So which means, so we can, and the specification hard disk drive is given, then we can calculate the average read time of the hard disk drive like this. So as you can see, the average read time is the millisecond time. Actually, very, very slow. So actually, because of this reason, so hardware just handles the data moving from DRAM, right? So actually, so if we just mention the processor architecture, then this processor just handle the data movement until DRAM. Okay. So and then what does that mean? Storage devices. The reading data from the storage devices are managed by operating system, not hardware. It is because the storage devices are much slower than the processor. So we handle the data movement between this DRAM and storage devices using software. Okay, the hardware just supports the data movement like the direct memory accesses. Okay. So I think I need to stop here. Then the next class, so we will learn about the basic of caches. So another announcement is that I will post the first homework assignment Blackboard today. So then this first homework will cover the pipelining. So this is the late part of the chapter 4. Then also this part is very important. So please start the homework questions by yourself. So as you know, the level of the homework questions are very similar to the level of the questions in the exam. No? Okay. So please try to start the homework question by yourself. Any questions? Thank you for your attention and see you in the next class.